Good day from Chem Help ASAP. In this video, we'll do a demonstration of a reaction that makes a heterocycle called a pyrazole. The video description contains links to supporting documents, including the laboratory procedure and proton NMR spectra. Here is a very old chemical reaction. It is the Knorr pyrazole synthesis. The reaction starts with two starting materials, a 1,3-diketone and hydrazine. Note that the hydrazine can have an R group on one of the nitrogens. These two reagents react and ultimately form a 5-membered aromatic ring called a pyrazole. A pyrazole is specifically a 5-membered aromatic ring that contains two nitrogens, and the two nitrogens are right next to each other. This reaction occurs through the loss of 2 molecules of water. The Knorr reaction is fast and normally gives a high yield of the product. Different types of the starting materials, the dione and hydrazine, are readily available for purchase through chemical suppliers, so you can quickly make many different pyrazoles with different R groups. The only negative things I'd say about this reaction is that the hydrazine and substituted hydrazines can be very toxic. If you've heard of hydrazine outside of a chemistry class, you've likely heard about it in the context of rocket fuel. Hydrazines are reactive, and you should protect yourself thoroughly from exposure to them. There are variations of the Knorr reaction. One variation exchanges the 1,3-diketone with a beta-ketoester. Swap an ester in place of one of the ketones. Beta-ketoesters react with hydrazine to first form a hydrazone as an intermediate. The hydrazone then reacts intramolecularly with the ester through an acylation to make a pyrazolone. The 5-membered ring product of this reaction has 2 feasible isomeric products. These products are tautomeric isomers, and they exist in equilibrium with one another. The first one I've drawn on the left is the pyrazolone form, the keto tautomer. The second one on the right is a pyrazole. It's the enol form. Historically, chemists usually draw the pyrazolone form as the product. The characterization data, however, more closely align with the pyrazole form. The reaction in this video shows the formation of a pyrazolone. Specifically, our ketoester is a molecule called ethyl benzoylacetate. And then the hydrazine will be regular, unsubstituted hydrazine, NH2, NH2. We'll perform this reaction on a small scale. We'll use about 3 millimoles of the ketoester. That will be the limiting reagent. We use an excess of hydrazine, about 6 millimoles, or twice as much as the ketoester. That's about 2 equivalents. The reaction is run in 1 propanol with a little bit of acetic acid and heat. The product forms quickly, and we'll just add water to force it to precipitate. It's going to work great. Okay, well, here we are at the balance, and I apologize for the light. It is earlier morning, and we're getting some shadows off of the sunlight coming in from the window. So here we have our reagent. This is the reagent we're going to measure first. This is ethyl benzoylacetate. This is our beta-ketoester, and we're going to weigh this out. Even though it's a liquid, we're going to weigh it out on the balance. So we need approximately 576 milligrams of this material. I don't care that we get exactly 576 milligrams, but I want to write down exactly what we do use. I just want to be in that ballpark. That's about 3 millimoles. So I'm watching the balance. That's around 200, 300. The suspense is incredible. 400. We're not going to do it on what I got there. That's 480 some. Let's get just a little bit more. 530, 40, 50, 573. A drop is about 10 to 20 milligrams. So let's try one more drop. And that is 500. Oh, why did I go over by that? Oh, well, anyway, it's 588 milligrams. We were at 573. So we will take this to the hood and see what we get. Set up the reaction. Okay, now we are in the hood. So we have our vial with 588 milligrams of our beta ketoester in it. We're going to want to heat up this reaction, and the solvent for the reaction is 1-propanol, and I have about 3 milliliters in this graduated cylinder, so I'm going to go ahead and add that solvent. Once I get the solvent added, I'll heat this up. So I'm going to heat it up after I add the solvent, because the hot plate is already warm. Hot plate's at about 120 degrees, and propanol boils at 1-propanol boils at around 100 degrees. So you might say, well, this is going to be too hot. It's going to boil away our propanol. Well, the temperature reading on the surface of the hot plate is not necessarily how hot this scintillation vial will get. But yeah, I just want this nice and hot, close to the boiling point, but not vigorously boiling, and I'll go into that in just a second. Okay, so that is our beta ketoester. It has now been dissolved in 1-propanol, and it's warming up to, let's say, approximately 100 degrees. So now I want to add 3 drops of glacial acetic acid. The glacial acetic acid, just make sure that we have a little bit of proton source in here just to facilitate whatever the reaction wants. I'm going to blow out these bubbles. I'm not going to count that, but there's good 1, 2, 3 drops. And you might say, wow, that is not very precise. Well, the fact is, this is just a catalyst, and it is just helping the reaction. If we have a little more catalyst, a little less, it's probably not going to make a big difference. But we just want to make sure that there are some acidic protons in there at the beck and call of our reaction in case our reaction wants it. Now, what we have last, let's bring it into frame, is our hydrazine. Very often when you set up a reaction, the last thing you add to the reaction is typically the most reactive thing. It's not always true, but very often is. And hydrazine, as our reagent, is the most reactive thing. Note that hydrazine is not the nicest material, so treat it carefully. I'm going to dispense it in this manner, but this is, we're going to measure it as a volume. And this solution is going to be measured out with a pipetter. And this pipetter only goes to 200 microliters. I need about 380 microliters of this reagent. And so I'm going to add it in 2 portions, 190 microliters each. There's 1 portion. And here comes the second one. And this is hydrazine hydrate. It is 51% hydrazine in concentration. Okay, great. So we have now dispensed our hydrazine reagent. And now, in theory, this is all this needs. So we have our beta ketoester in there. We have our solvent, 1-propanol. We have 3 or so drops of acetic acid as a catalyst. And we have our hydrazine. So since this is warming up, I'm just going to gently place the cap. I'm not going to screw it down. I'm not going to seal it, because this is, after all, it's heating. We don't want it to get hot and expand and generate pressure in there. So just by placing the cap on there, we're allowing this to interact with the environment and not build up pressure. But this is going to heat. This is going to heat for about an hour, and then we'll come back and likely take a TLC and see if we're done. Well, here we are where we left off. We've heated this for about an hour. You can see there's some color change here. It's got a little bit of an orange color to it. I didn't point this out, but when we cut off from the video previously, you can scroll back to see this, you'll see the reaction was starting to yellow just a little bit, even in the short time that we saw it react at the very start. So this color change has been progressing a little bit. Remember that we did this and we didn't want this to really, we wanted it to heat but not vigorously boil. And this clearly hasn't boiled away to dryness at all. And there is, it's hard to see in the camera, there is a little bit of vapor condensation on the sides. I'm not sure that's coming through. That's a good sign we're getting some heating, but not overly vigorous heating. So again, the hot plate says 120, but that doesn't mean the reaction actually reaches that temperature. And as we have airflow in the hood, it cools the sides of the vial, and that helps us condense and recollect those vapors and return those to the reaction mixture. So, okay, well, what is the next plan? Enough talk about what we're seeing. What are we going to do? Before the reaction is complete, we really ought to have a check and see if it's complete, and we'll do that with a TLC. So I'm going to go off camera, I'm going to take a TLC, and we'll look at those results. Here is the TLC of the reaction mixture. The mobile phase is 30% ethyl acetate, 70% hexane. This is a classic 3-lane TLC. On the left, we have one of our starting materials. I spotted the ketoester, ethyl benzoyl acetate, as it is our limiting reagent, and it shows up well under UV light. In the middle, we have both the starting material and the reaction mixture. On the right is just the reaction mixture. The key thing to notice is that we do not see any starting material in the reaction lane. If there's no starting material in the reaction, then this reaction is probably finished. We do see a blob at the bottom of the plate. This blob is likely our product. Great, so after 1 hour of heating, this reaction seems finished. Okay, so that TLC plate looks really nice, so we're ready to stop this reaction. Note that everything is still dissolved. In fact, it's still hot on the hot plate, and while it's still hot on the hot plate, I'm going to add some water to this. So the water is going to increase the polarity of our solvent. Our product is going to precipitate out, and you can see it's actually starting to precipitate out before our eyes. So let's go ahead and add the water before it happens too quickly. And that is just fortuitous timing right there. Okay. So it may be that it was saturated, and just the action of moving it on the hot plate caused it to begin precipitation. But we'll go ahead and get this water added in. And now the polarity is certainly high enough. That product is precipitating out. You can see that it's gotten white. It's gotten white because it's got a lot of solid that reflects the light. And that makes it look brighter and whiter. There we go. Now, I was going to let this sit on the hot plate so that the hot plate, as the hot plate cools, let's turn that off, then that would allow this thing to slowly cool, and in case it oiled out, it would slowly solidify. But as you can see, it's formed solid great. Spinning around, we got lots of solid. That looks really good. We know there's no starting material, so I'm just going to let this cool on the hot plate with stirring, and maybe in 30 minutes it'll be close to room temperature, and then we can go ahead and do a filtration to isolate our crude product. Alright, everything is cooled down nicely. If you notice, it's kind of interesting, this reaction mixture has gone from looking kind of orange to almost a little bit pink. So that's kind of unexpected. I wouldn't put too much stock into these color changes, but it's important to observe them. If you were to run this reaction and it didn't turn that same shade of pink, I wouldn't worry about it. But still, it's organic chemistry is full of colorless liquids and white solids, so it's always fun to see a little bit of color. Now we're ready to filter this material, and we're going to use a Knorr funnel. And what I'm going to do is I'm going to turn on the vacuum. We've got good suction, and we have a filter paper in there, and that filter paper should cover all the holes, and it does. So I'm going to seat the filter paper. You always need to wet the filter paper with a solvent that's very similar to what you have in your mixture, and it's over 75% water. So I'm going to seat this filter paper with water. And now I'm just going to take this and dump it in. And that's great. All that color is going through. The solid is staying in the funnel. Let's rinse this with a little bit more water. And this is a great reaction because aside from our one main starting material, the beta ketoester, everything else should be water soluble. We have excess hydrazine, but hydrazine is water soluble. We have excess acetic acid. Acetic acid is water soluble. So everything ought to go through the funnel and leave behind our product. So this is now filtered. There's nothing more to it than that. So we'll go ahead and I will let this material in the funnel air dry. Then we'll get a mass and we'll see what kind of crude yield we got for that. And of course then we'll need to make sure it's pure. We'll take an NMR, get a melting point, take a final TLC. Okay, well it is now a day later and I have taken the filtered solid, spread it out on a piece of weighing paper to dry, and this is now 390 milligrams of this nearly colorless, I'll just call it white solid. And that is our product. And I haven't calculated the percent yield, but that is, I think, a fairly reasonable yield of this product. So now, of course, we have to see, is this solid, this very promising looking solid, is it actually any good? So we need a TLC of this material, we need a melting point, and we need an NMR spectrum to characterize this material and to see if we made what we expected. So initially everything looks promising, but let's see what the data say. Let's start with the TLC of the isolated product. This TLC was performed in 100% ethyl acetate. Remember the blob from the previous TLC plate? To get that spot a little bit higher on the plate, I changed the mobile phase to something more polar, like 100% ethyl acetate. This TLC looks great, just one spot. Remember that this product is technically a crude product. We have isolated the product through a precipitation, but it hasn't formally been purified through chromatography, distillation, or recrystallization. So for a crude product, this single spot is very encouraging. The RF value is approximately 0.40. Now, seeing just one spot does not mean the material is clean, but at least it's a good start. The melting range for this product was 242 to 244 degrees Celsius. The melting range for this product is somewhat interesting. If you look up references for our product, most report a melting point of 236. It's rare to get an experimental melting point that is higher than the literature value, but this compound also has a reported melting range that go into the 240s and even 250. That may seem crazy. How, in the name of chemistry, can reputable scientists possibly have different values for a melting point? Well, it happens, especially with melting points. Since there are many melting points reported, I'll go ahead and choose a literature value that is close to what I observed, 238 to 240, taken from the reference at the bottom of the slide. Regardless of my capricious selection of a literature melting point, the product is one spot by TLC and has a sharp melting range. Those are both good signs of product purity. Finally, let's look at the NMR spectra. On the screen is the full NMR spectrum. The spectrum was taken at 400 megahertz in DMSO. That's deuterated DMSO as a solvent. The residual peaks from our solvent are at around 2.5 ppm. That's DMSO itself, and at about 3.5 ppm for water. So we can ignore these peaks while interpreting our spectrum. As we look across this spectrum, note that there are very few blips along the baseline. That's a sign of a very clean product. Let's go ahead and zoom into the part of the spectrum that shows our peaks of interest. Here is a more tightly zoomed in spectrum. All these peaks now have integrals. I did not do the best job on these integrals, but we can still get the information that we need from them. Remember that our integrals are interpreted as a relative intensity. not the absolute number under the peak. So our leftmost peak has a value close to about 0.75. This is not 3/4 of a hydrogen. This is 1 hydrogen. So our leftmost peak is 1 hydrogen. So for the rest of the spectrum, for every 0.75 value of integral, we know that equals 1 hydrogen on our molecule. The next signal is about 0.75. That's also 1 hydrogen. Next is about 1.5. That's 2 hydrogens. Another 1.5. That's 2 hydrogens. Here's another close to 0.75. I obscured it a little bit. That's 1 hydrogen. Finally, a give or take 0.75. That's 1 hydrogen. In total, our integrals show 1, 1, 2, 2, 1, 1. That's 8 total hydrogens. Our product also has 8 hydrogens. Wonderful. I've shown both tautomers of our product to the left. The NMR will help us identify which tautomer is favored by our product. Let's first eliminate considering the hydrogens on the phenyl group. Those 5 hydrogens appear together in the middle of the spectrum in the 7 to 8 ppm range. Aside from these hydrogens, our product, regardless of which it is, should have 3 hydrogens. For the keto form on the top, we would expect just 2 signals. The NH would be a signal. The CH2 should be a signal, a 2 hydrogen signal. The enol form should give 3 signals, 1 for the NH, 1 for the OH, and another for the CH. How many signals do we see in our spectrum beyond the aromatic hydrogens? We see 3, and they have a relative intensity of 1 to 1 to 1, so our spectrum clearly favors the enol tautomer as the correct structure of the product. Regardless, traditionally, chemists show these molecules in their keto form. We'll follow the standards set by others, but this compound is more accurately viewed as the enol tautomer. Here is one last spectrum. It's an expansion of the aromatic region. The integration of these peaks shows 2, 2, and 1 hydrogen. The doublet is from the hydrogens closest to the pyrazole ring, the ortho hydrogens. They have 1 neighbor, so they are a doublet. The triplet is for the meta hydrogens. They have 2 neighbors and are therefore a triplet. That leaves our lone para hydrogen. It has 2 neighbors and is a triplet. That completes our tour of the NMR spectrum. Everything looks great. Let's finish with a yield calculation. We started this reaction with 588 milligrams of ethyl benzoyl acetate based on a molecular weight of 192.21 grams per mole. We had 3.06 millimoles of our ketoester. The hydrazine will be a bit more work. We used 380 microliters of aqueous hydrazine. Since we use the volume, we need to use density to convert that volume to a mass. Aqueous hydrazine has a density of 1.00 grams per milliliter. Following some unit conversions, that works out to 380 milligrams of our aqueous hydrazine. Aqueous hydrazine is 51% pure. That's 51% hydrazine and 49% water. So that means we added 194 milligrams of pure hydrazine. That's 51% of 380. Hydrazine has a molecular weight of 32.05 grams per mole. That is 6.05 millimoles of hydrazine. Our limiting reagent is ethyl benzoyl acetate. The number of millimoles of ethyl benzoyl acetate is our theoretical yield. What is our actual yield? Well, we got 390 milligrams of product. The molecular weight of the product is 160.18 grams per mole. That means our actual yield was 2.43 millimoles. Actual over theoretical times 100 gives us a 79% yield. In addition to a high yield, we have confidence that the product is also fairly pure based on seeing one spot by TLC, a sharp melting range, and essentially no impurities by NMR. I hope this demonstration of Knorr's pyrazole chemistry was interesting to you. Check out the video description for links to the procedure and NMR spectra for this reaction. Please subscribe, like, or leave a comment. Take care.